folks, hopefully the videos I've set this week prior to this one will have made perfect sense to you. But I just wanted to scoot through the first part of these notes, just highlighting a few things that are important for you to know, and also that maybe leave a little bit of ambiguity or that pupils have struggled with in the past. Don't get hung up on the Niels Bohr model of the atom. It's the same one that you've been using since Nat 5 when we looked at just electron shells. So for example, when you were drawing these kind of diagrams where you've got a carbon atom with 6 electrons and you had shells, 2 shells, that's the Bohr model of the atom. Nothing's changed with that. So, by now you will have gathered that things are going to get a little more complex, and we're adding on to the atom, or our knowledge of the atom, which hasn't changed since National 5. Except that when you add a little bit of knowledge, things quickly seem like they're going out of control and things start getting a bit, I don't know, difficult to understand, but it's not really as difficult as you might think if you break it down and look at it carefully. So, it's all about quantum mechanics, and we have been talking about the quantum numbers and atomic orbitals. It is really important that you are aware of these 4 quantum numbers and also their letters or their symbols. N is just the shell, the same as the ones that you were in National 5. The angular momentum number is the shape of the orbital that it's held in. So is that an S, a P, a D or an F orbital? The magnetic quantum number signifies which of those orbitals it's in. So for example, if an electron was in a p orbital, is it in px, py or pz? And the spin magnetic quantum number is just about whether or not it's spinning in one direction or the electron is spinning in another. So these 4 numbers are kind of used almost to give a house number and postcode for an electron, which is very unique, or is totally unique to that electron. So here we have our first set of pictures for orbitals. They're perfectly spherical. We've got the 1s, the 2s and the 3s orbital. Because they haven't changed since National 5, you are not going to be asked to draw these. You're not going to be asked about them really, because you don't need any extra knowledge for advanced higher to be able to answer any questions on them. These px, py and pz, you need to know. Not only do you need to be able to identify them, and I mean identify them in terms of this one here is py because the lobes of the orbital are cut through by the y-axis. You have to be able to draw them, and you have to be able to draw them with enough information for people to realise that you are drawing the correct one. So if I was asked to draw PZ orbital, I would draw my axes. They would be labelled, same as in maths, X, Y and Z. And then to put on my PZ orbital, I would have to ensure that I drew a dumbbell shape, but also that it was cut through by the by the Z axis. So that is orbital PZ. The d orbitals are far more complicated. You'll not be asked to draw them. But what is important about them is that all the ones that have the two letters, the XZ here, or the YZ, or the XY, lie in between those axes. So not within them, but they're almost rotated to 45 degrees between the two axes. The one that's dx squared minus y squared is on those x and y axis, so it's like a double dumbbell shape, or it's like two p orbitals combined, but on the x and on the y axis. And the dz squared one is the one that's most noticeable, the kind of dumbbell plus donut shape, and that one's really quite obvious, but because it's one of these ones that's got the squared in it, it's on the axis. Although you won't be asked to draw those, you will be asked to name them specifically when given a picture. The F orbitals, they look hideous. You'll be pleased to know that you don't either have to name them, nor do you have to be able to draw them. But what you should be able to do is, if given a picture, you should be able to tell the SQA that that's not a S, not a P, not a D, but it is an F orbital. The answers to the quick test. The quantum number which specifies the shape of an orbital is B, the angular momentum quantum number. A helium atom has 2 electrons in its ground state. One of the electrons can be described by the 4 quantum numbers 1, 0, 0 plus a half. The other one, it's really simple when you get these. All you need to do is change the sign on the spin. The term degenerate is a term that you do need to know, but that means of equal energy. Electronic configurations. I'm going to go into a little bit more detail on these because I haven't managed to find myself a video that has explained these particularly well, or at least that hasn't explained them the way that we would want the electronic configurations to be explained and what you will get asked to do in an exam. Most of the videos are American and they have different ways of showing what we're doing here. So, there are 4 rules that you're going to need to know about. Heisenberg uncertainties principle, that was covered a few pages earlier. It's officially no longer in the course, but the problem is that there are 3 other rules. Pauli's exclusion principle, the Aufbau principle, and Hund's rule of maximum multiplicity, which only leaves 3 answers for a multiple choice, so quite often they'll throw in the theory behind Heisenberg's, so it's useful if you do know what it is. But Heisenberg's uncertainty principle is essentially, we don't know exactly where an electron is, but we're pretty sure it's in that area there. Wolfgang Pauli proposed what's now known as the Pauli exclusion principle, where no 2 electrons in any one atom can have the same 4 quantum numbers. That was shown in the answers to the quick test, where we had to change the last number so that the first 3 quantum numbers would stay the same, but that last one was different. So that leads to 2 important conclusions. 1, the maximum number of electrons in any atomic orbital is 2. if there are two electrons in an orbital, then they must have opposite spins other than parallel spins. When we're talking about spins, we really are talking about the spin on an electron. So if we imagine we have two little electrons here, and if we put a pole through those electrons, then one electron may well be spinning anti-clockwise, and the other electron may well be spinning clockwise. And to each of these, although we don't distinguish between them, we could have a plus a half or minus a half for that last part of the quantum number, or the spin quantum number. The number of electrons, or number of orbitals and electrons in each subshell is given in the table below. There are only 2 electrons in an s orbital. There are 6 electrons in a p orbital, because if we look back to the diagrams of our p orbitals, then we can have 2 electrons in this one, 2 electrons here, and 2 electrons here. Our 5d orbitals, for the same reason, gives us 10 electrons. So we can have 2 electrons in here. So we would tend to have 1 in this area and 1 in this area, and so on all the way through. But even though there's this double dumbbell shape, that does not mean that 4 electrons will occupy this. It's still only 2 per orbital. And back to this hideous diagram here. There are 7 f orbitals. Each of these orbitals holds only 2 electrons, regardless of how complex this diagram looks. In an isolated atom, the orbitals within each subshell are degenerate. For example, the 3 different p orbitals, px, py and pz in an atom, have equal energy. There are 2 main ways in which the electron configurations of atoms can be expressed. One of these ways is the same way as was shown in the videos, and the other way is different. So I need you to pay attention to this bit. If we have a look at a hydrogen atom, it only has 1 electron. The lowest energy out of all of the orbitals is the 1s. So our 1 electron can be expressed as 1s1. For helium, there are 2 electrons, it's still the s orbital. So it's the first shell, s orbital, 2 electrons are in it, so this would be 1s2. When it's written like this, it's called spectroscopic notation. The other way in which the electronic configuration can be expressed is using a notation which an arrow is represented by a box and each electron by an arrow. In the videos, they were using lines, where they had a collection of lines that looked a bit like this. And they were filling them in like this. But my worry is that this is not okay. It's not okay for chemistry because of this shape here where they're drawing an arrow like this. There's an overarching theory in chemistry where when we're drawing an arrow, apart from the reactant A plus reactant B heads off to make C and D, we use arrows in advanced higher chemistry for electrons, and we'll use them in this unit and we'll use them in the organic unit. So it's important that we always understand what the arrows are all about in chemistry. The reason I don't like this arrow here is it's got the double head on it. It looks like a single head to you. I'm sure we would call that a double head. And that double head would signify 2 electrons. Where what we want is 1 electron. So it only has 1/2 of the arrowhead on it. They can be drawn in that direction, or they can be drawn down, but that's called a fish hook arrow. Fish hook arrow. And it signifies 1 electron. So this situation in these diagrams is worrying because a lot of them were showing this looks like, as far as I'm concerned, that looks like 4 electrons, not 2. Whereas, had they drawn it like this, that would be 2 electrons. The other issue is that we don't draw these diagrams like this. What we draw is something called an orbital box diagram. So for hydrogen, we draw a box for the first orbital. It's orbital 1s and it's got 1 electron in it, so that would be 1s1. You don't need to put the 1 here because it's shown as 1 electron. Helium, it's 1s, but there are now 2 electrons, and note that they have been added in with their spin opposite to each other. So one arrow pointing up, the other one pointing down, in agreement with Pauli's exclusion principle. If the electronic configuration of helium was to be represented with both arrows pointing in the same direction, i.e. parallel spins, this would be incorrect. It would not conform to the Pauli exclusion principle because the 2 electrons would have the same values for all 4 quantum numbers. For helium, so drawing the Bohr model of the atom, what we're saying is we're in the first shell of electrons. So n equals 1. The shape is 0, or L equals 0, because it's an s orbital. There's nothing complex about that first, hydrogen and helium. You don't have an option of which s orbital because there is only one. So Ml gets the value 0, and one of these electrons will be plus 1/2 and the other one will be negative 1/2, but it doesn't actually matter which one you assign to which. So we have our 4 quantum numbers. So this helium atom could be given the quantum numbers plus 1/2 and minus 1/2. Before we can write electronic configurations for the multi-electron atoms, it's necessary to know the order in which the various orbitals are filled. This is the Aufbau principle, and unlike in the videos where they gave this a capital A, this is not a typo. It means building in German, so because of that it doesn't have a capital letter. It states that the orbital of the lowest energy are always filled first, which you knew from the Bohr model of the atom, because we always filled the inner shell before we moved on to the next one and on to the next one. So, if you know the relative energies of the orbitals known, the electronic configuration can be worked out. Spectroscopic data gives the following arrangements of the energies of the electrons. So 1s, 2s, 2p, 3s, 3p, 4s, 3d. Oh, that looks strange. From National 5 and higher, we would have thought that we would fill all of the third shell before the fourth shell, and that's not the case. So we've got our first shell of electrons here, our second shell fills here, our third shell is filling here, and then we've got this fourth shell that doesn't get finished until here, but there's been some of the fifth shell and the sixth shell getting filled in between. So this is why we never went any further than 20 elements in National 5 and higher, because then you didn't need to deal with this, what appears to be randomness. So what we're essentially saying is it's not always filled. An atom's not always filled from the inside out. It is for the first 20, and then things start getting a little bit more complicated. This order you need to know, and it looks horrible, but there's a cheat, as always for chemistry. And the cheat is, if you start up here, you can draw lines through, always hitting the S diagonally, and this gives you the same order. So 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 3d, 4p, 5s, 4d, 5p, 6s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 4f, 5d, 6p, 7s. And that's the way that you reckon, or you remember this order here. It's quite a common multiple choice question where they will shuffle this, and the only way I can recommend is quickly sketch this out, this diagram. If you remember, every shell always has an S, then a P, then a D gets added in by the time you get to the third shell, and when you get to the fourth shell, you get your F. And this arrangement would complete the periodic table as it is just now. When the situation is reached where more than one degenerate orbital is available for that electron, it's necessary to use Hund's rule of maximum multiplicity, which states that when electrons occupy degenerate orbitals, the electrons fill each orbital singly, keeping their parallel spins before pairing occurs. You've kind of been doing that since National 5, because when we were drawing electrons, if this is our nucleus, then we never paired these two. But you weren't wrong if you did. Please excuse my circles. But when filling in the next 4 electrons, you placed them in singly before then pairing up. So you didn't know at the time, but you were following Hund's rule of maximum multiplicity. Using all the rules we've encountered, so that's Heisenberg's uncertainty principle, as in we don't exactly know where they are, but we can work out roughly where they're going to be. Pauli's exclusion principle, that no two electrons can have the same 4 numbers or the same 4 quantum numbers. The Aufbau principle, we start 1s, 2s, 2p, 3s from the lowest energy and build up, and Hund's rule of maximum multiplicity, which is we fill shells or we fill orbitals singly before we start pairing up. We can have a look at now nitrogen, which has 7 electrons. Up until now, its electron arrangement would have been written as 2-5, as it was in National 5 or higher. That shows that hydrogen has 2 shells of electrons, 5 electrons in its outer shell. However, taking into account the more in-depth advanced higher atomic orbital knowledge, the electronic configuration of a nitrogen atom can be written as shown, using orbital box notation. So we have 1s, 2. As I said, you don't need to have these numbers in. You're not wrong if you add them. So the 1s orbital is just one box where 2 electrons fit. The 2s is one box because there are only one type of 2s orbitals, or it's only one s orbital. The 3p has 3 boxes because it signifies px, py and pz. Or you can write them this way up, but this way is by far the most common way to see it and the way that the SQA would show you. This one's a little bit more like the diagrams from the other videos. So this is orbital box notation, and this is spectroscopic notation, where you don't have the boxes in. If you're asked for orbital box notation, you have to label them. You have to label them accurately, or you would be marked wrong. If you leave them unlabeled, you get marked wrong. Using spectroscopic notation, the 2-5 would now be written as 1s2, 2s2, 2p3. You can still see in the second shell there are 5 electrons. The last video that I sent you was on this shortened version, but hopefully now that we've gone over this a little bit more, this should make more sense. So this 1s2, 2s2, 2p3 for nitrogen can be shortened to helium, 2s2, 2p3, because helium is the noble gas just before nitrogen. If you look at the periodic table, and we have hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, and we have a look at nitrogen. Nitrogen spectroscopic notation was 1s2, 2s2, 2p3. However, if we look back, we can see that hydrogen's was 1s1 and helium's was 1s2. So nitrogen, we can take out our 1s2 and just use the electron arrangement of helium, and then say that we've got helium, 2s2, 2p3, which is the shortened electronic configuration. It doesn't seem like this is saving us much time, because we've got 1s2 here and square brackets with helium here. But when you move yourself further down the periodic table, it means you're never really accounting for any more than 18 electrons past your last noble gas. So we've got some further examples down the bottom here. Having a look at neon. Neon's electron configuration is 1s2, 2s2, 2p6. Argon's 1s2, 2s2, 2p6, 3s2, 3p6. So the electronic configuration of sodium, which is 1 past neon, 1 electron past neon, can be written as square brackets neon 3s2, square brackets past neon 3s1, where the square brackets with neon represents the 1s2, 2s2, 2p6. So hopefully now you can see why it really is shorthand. Calcium can be written as argon 4s2 instead of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. It does save a lot of time, but you need to be careful to find out in the question, have you been asked for the full one, in which case you have no option but to write the full string of numbers, or have you been asked for the shortened one, in which case this situation would be allowed.